right. Good morning, everyone. My name is Piero Canepa. I'm in Material Science and Engineering, and today, together with the sponsor of the Center of 2D Materials and the Material Science Department here at the National University of Singapore, I'm very glad to host the opening talk of this series called Materials for the Future. And of course, I'm very glad that Antonio Castroneto could sponsor this together with my department, and Shafiq Adams who's online, Marilyn, and many other people that has contributed to organizing this together to me and setting up the technicalities. Now, the speaker, I have a long relationship with the speaker. I met her in 2012. She's Christine Persson from Berkeley National Lab and University of Berkeley, California. She had a PhD in theoretical physics from the Royal Institute of Technology at Stockholm. And she's now a professor at UC Berkeley and a senior faculty scientist at the Lawrence Berkeley National Lab. Most importantly, she's the director and co-founder of the Materials Project, which is perhaps the most visible material genome initiative of the material genome, spearheaded by the United States almost a decade ago, if no more. And she's an associate editor of Chemistry Material, a journal that most of you in the audience know, as well as she has a number of prizes, including the Department of Energy Secretary of Energy Achievement Award, TMS Award in 2017, and many other things. She led a company, or she was in the board of a company called Pelion that deals with magnesium batteries and so forth and so on. She has more than 200 peer-reviewed publications. So today's talks is data-driven design for energy materials. The floor is yours, Christine. Thank you very much for coming here to Singapore virtually. I hope we can get you here in 3D, real 3D one day.
Me too. Thanks so much, Piero. I love coming to Singapore. So whenever we can do this safely again, I'll be right there on the plane. And thank you for the kind words. I'm really excited to kick off the seminar series and to talk about what my group does in the realm of data-driven design for energy materials. There we go. Okay, so for you who are in the audience that may not have seen the whole trajectory of where simulations come from, the reason we can do data-driven materials design today using computations, talking to experimentalists, is because there's really been a paradigm change in the last 20 years. When I was a graduate student back in Stockholm, as Piero mentioned, in 1996, I spent a whole year on calculating the phonon dispersion curves of tungsten. So one element, one property, many different volumes of the same element, but still one property, one element. And it took me a whole year because I had to fit the pseudopotentials, I had to parallelize a plane wave code and a linear response code. So the infrastructure wasn't there. And more importantly, the computing power wasn't really the same as today either. So if we now fast forward 20 years, 25 years to 2021, we now have calculated as an example of the databases that Pierre talked about, 130,000 plus materials in the Materials Project that's available for anyone to browse, with millions of associated materials properties. And some of the examples I give here in the lower bar are supposed to speak more to energy materials. So for example, you can browse intercalation electrodes, conversion electrodes. You can find out whether your materials are likely to decompose when exposed to moisture. You can examine redox molecules for flow batteries and solid state interfacial reactions relevant for solid state batteries. So these are some of the associated analysis algorithms you can put on top of the data you get from the calculations. And this really explodes exponentially once you're able to calculate all these different things. So I'll just have one slide on showing the three projects I'm going to describe to you. I'll try to sort of highlight how my group operates and what we do. And a lot of this is common for many other computational groups as well. You obviously start with an observation, and usually that observation is some experiments. For example, let's say, okay, there are very few stable magnesium electrolytes. Why is that? Why is that so much harder than lithium electrolytes? And then you sit around and you think and you look at it and you go like, okay, well, you come up with some hypothesis. And you may come up with a hypothesis like, okay, there's got to be some difference in charge transfer when you're dealing with an electrolyte that has a divalent cation compared to a monovalent cation. Can we explore that and how the speciation in those electrolytes look? Now, the third part, my group tends to develop workflows. We don't just go and calculate for one system. We tend to go like, okay, let's calculate for 10 systems or 5 systems or 30 systems or, God forbid, 1,000 systems. So we tend to develop workflows, put our analysis algorithms into PyMatGen or associated software, and make sure that this is somewhat reproducible if you come from the outside, if you're not part of my group. After that, after the data production stage, you design your workflow, you make sure it's robust, you test your hypothesis by calculating a lot of data and analyze that. Hopefully you come to the point of insights. Hopefully, not necessarily. You may have to go back to the hypothesis and reiterate that for a while. But you come to an insight where you compare the results from your calculations with the observations that you started out with, and maybe you come up with something really cool. And if you come up with something really cool in the sense of explaining why something happened, and maybe you validated your hypothesis, now you can go to the design stage. Like, can I now change materials to become better than they were to address the fundamental issue that I first identified? And then the 6th stage is really, okay, I've had an insight, I've produced data, I've produced algorithms, I've come up with new materials. Can I also disseminate this in an effective way to the broader community so that next time somebody does this or something associated or related, they don't start from scratch. They start from existing data or existing algorithms. So if I were to sort of call out, I think a lot of groups operate similarly. We all start hopefully with an observation. We hopefully all come with a hypothesis. But the data production, the design and dissemination is something that we take very seriously in my group. Also because we house the materials project. So the data production and dissemination come very naturally to us. So I'll try to highlight these aspects as I go through these examples. 3 of them. The first one is on design of multivalent electrolytes. And this was very much what I sort of gave a little bit of a talk, or like I used as an example in the previous slide. And this one I will take all the way from observation, data production, design, and coming up with new materials. And then the next one will be about coatings in cathode materials, which is a little bit less mature. There we've gone to an insight, and we're currently working on the sort of design stage of novel materials. And the third one is really in the production and analysis stage, and that's on the SEI of electrode materials. But first one, the multivalent electrolytes. So if you go to any paper, most of the time, and you look at lithium ion or sodium ion or some sort of ionic electrolytes, you typically find pictures like this, where you have your active cation, for example, lithium, being solvated mostly by solvents. You don't really normally see a salt in there. So this is the picture we started from when we started looking at multivalent electrolytes back in 2010, 2011, when we were interested in them. So the first thing my team did was just figuring out, is this what multivalent electrolytes, magnesium, calcium electrolytes look like when at like normal operating battery concentrations, 0.5 to 1 molar. So it turns out that not even lithium electrolytes really look like this if you look closely. Yes, the majority species in a lithium 1 molar electrolyte is what you see there on your left. It's the lithium being largely solvated by the solvent, but that's the majority species. The anion, the PF6 anion, is hanging around somewhere. But there is a minority species too, or several minority species that are in equilibrium with the majority species. And that's, for example, the contact ion pairs that you see there on your right, where the lithium is solvated not only by solvents, but also by its anion. And that's not a neutral species. It doesn't contribute to conductivity, for example, but it can contribute very seriously to things like the electrochemical window of your electrolyte. So these minority species may be, in many cases, overlooked, but they can actually be the limiting case when you look at the properties of the electrolyte. Because even if it's the minority species that decomposes, that equilibrium will keep on feeding the speciation in the electrolyte. So one of the things we set out to make sure in the beginning that we took into consideration both the majority and the minority species. In multivalent electrolytes, it turns out that the majority species are not the same as in lithium electrolytes. Our first simulations on this classical system of magnesium with diglyme and TFSI as the anion turned out to, even at 0.4 molar, which is much lower than commercial lithium-ion electrolytes and concentrations, is the majority species is contact ion pairs. So just having the anion, in this case TFSI, being part of the first solvation sphere. We were so surprised by this that we slightly doubted our models, and we went to our colleagues at the APS and asked them to do X-ray on the electrolyte and figure out whether this was actually true. And what you're seeing there is the radial distribution function correlating to the solvation structure that was measured at the APS. So indeed, yes, the majority species in magnesium TFSI at 0.4 molar is contact ion pairs. It's not completely solvated magnesium ions. So what does this mean in terms of its performance? So in the normal electrolyte, when you have largely solvated species, and you're trying now to plate. So in magnesium electrolytes, you want to plate your magnesium on the magnesium metal. If you're just solvated by solvents, you're going to strip those solvents at some point, and you're going to be done. But if you're solvated by an anion, that anion has a very strong electrostatic bond to your cation, and it's likely to be the last remaining delivery vehicle when you come close to the anode interface. And there you're supposed to take up electrons, so you're actually plating on the metal interface. What happens to that anion? Is it stable? In general, even if it's not an anion, if it's a solvent, is that stable under those plating conditions? And that was the question that we asked ourselves, given this new understanding that our solvation structure is quite different than for monovalent electrolytes. What does that mean for the stability of the solvation sphere of the different species? So we did bond dissociation energy analysis, and now we're looking into quantum mechanical calculations. So we're doing first principles calculations. We're breaking different bonds in the different molecules. So first, starting out with just TFSI, the anion, is it a stable molecule to begin with? I mean, that's kind of trivial because people use it all the time. It's actually considered very stable. And yes, indeed, nicely, our calculations confirm that our models can reproduce that we have very strong bonds in TFSI by itself. If you look at TFSI together with magnesium 2+, so if you just dissolve the salt in the solvent and these two guys are hanging out together, are they happy, or are they, doing something bad to each other? Again, TFSI is very stable, very strong bonds. But if you look at what we would expect to see at a small amount of time, as the magnesium gets closer to the anode interface, it has to, very differently than lithium, take up 2 electrons, right? And it's very unlikely that in all cases, those 2 electrons come at exactly the same time. They're likely to be, sometimes it's once, and then it's a little bit of a window, and then comes the second one. Okay, now assume that you get just 1 electron for a small amount of time. The beauty of simulations is that we can freeze that time window, and we can examine what happens to the bonds in TFSI when it's for a very brief time exposed to magnesium 1+. Magnesium 1+ is a horribly reactive species. It hates being magnesium 1+. So it subjects the solvation sphere, the molecules around it, to a tremendous electrochemical pressure. TFSI can't keep up with that. And that's what you're seeing in the middle bond dissociation energy graph, that when TFSI is associated with magnesium 1+, one of its bonds, the CF bond, breaks catastrophically. So that's where it decomposes. And that's the fundamental difference between lithium or monovalent systems like lithium electrolytes, sodium electrolytes, where you only have to take up the 1 electron, you plate your atom, and you're done. You're done with your charging of your battery. But in multivalent electrolytes, you have to do this 2 electron or sometimes 3 electron process if you're dealing with aluminum. And that subjects your solvation sphere, your molecules around your cation, to a high amount of electrochemical stability demands. So TFSI, we figured out, okay, we think that this is why TFSI doesn't work so well for magnesium, plating on magnesium. But this is not enough to validate the hypothesis, right? So we go and look at another salt that we know experimentally actually works quite well on the anode side. It has a very low oxidative stability, so it's not something that can take us to commercial success for magnesium batteries, but it does have a very stable plating performance. So we did the same analysis on borohydride, magnesium borohydride, and it turns out that yes, indeed, borohydride is stable when it's associated with magnesium 1+. So different than TFSI. And we looked at another salt that was recently proposed in those days. In 2015, the monocarborane, which retains the same motif of borohydride motif as the just single borohydride, was pioneered by Toyota. We took that carborane and we analyzed it from the same perspective. Are there any bonds in the monocarborane that would be unstable under association with magnesium 1+, and indeed it's still stable. Again, validating that this is hopefully a good descriptor for stability for magnesium plating and other multivalent plating mechanisms as well. Okay, so we think we have an insight. We're now at the insight stage. We're saying, we have a descriptor for stability of magnesium salts or anions under plating conditions, which is a big deal, because if you can predict that, you can go and predict novel salts, and you can tell experimentally you should take this salt because we decided that this is probably stable. So we're now testing this one on the design stage. So we took the monocarborane and decided to see, can we expand its electrochemical window? Can we make it more oxidative, increases anodic stability, so make it more stable under oxidative conditions? And the one way of doing that is to functionalize it, to change the ligands and to explore different functional groups. So we took 50 different functional groups, again, something you can easily do from computations, because we can crunch through so many computations in a short amount of time. And we tested whether they would still be stable under plating conditions, so stable under magnesium 1+ association, but also is it going to be higher oxidation stability than the original carborane? After those selection criteria, we came up with about a handful of functional groups that fit those two criteria. And then we talked to our experimental colleagues and said, which one do you want to try to make? And of course, they chose one of the simpler ones, because it's not easy to make new materials or new molecules. So the simplest one for them to make was the 1-fluorinated monocarborane that I'm showing there at the upper right-hand corner, which we had predicted to both retain its stability for metal plating, as well as having about a 200 millivolts improvement in oxidative stability. So this molecule was made by Nathan Hahn and Kevin Zavadil at Sandia Laboratories. Took quite a while for them to make it and purify it. This is not easy stuff. And indeed, but as you can see, as the curves down at the bottom show, the red curve is the fluorinated version. It does indeed have the oxidative wave at a higher voltage, about 200-300 millivolts higher. So the predictions worked. You could argue that 200-300 millivolts isn't going to save the day, but it's something. It did show that our sort of insights were valid to some degree. Another way we've taken these insights is that another way of improving the stability of anions or salts in multivalent electrolytes is just making sure that that anion doesn't hang out with the cation at all. So TFSI, even though we normally consider it a weakly coordinating anion, is actually fairly coordinating with magnesium. So we designed in the Joint Center for Energy Storage, we designed these large fluffy anions that didn't want to associate it with any multivalent cations at all. The first one being this TPFA that you see there on your left-hand side. And you can see the delta G for association. And it's actually a minus 0.4 EV for TFSI. And as you go up to the monocarborane, it becomes a little more dissociative. It doesn't like to hang out so much with the magnesium. And when you're at TPFA, this is such a minority species of magnesium that is contact ion pair, they're almost negligible. And indeed, this salt too, these highly weakly coordinating salts have shown to be both higher in oxidative stability as well as metal plating conditions. Similarly, another weakly coordinating salt was pioneered by Linda Nazar's group at Waterloo. This is a calcium salt, which also has this idea of being extremely weakly coordinating so that the solvent, the environment that delivers the cation to your interface is now the solvent. So the pressure is on the solvent to stay stable, but that's another story. You can ask me questions about that later if you're interested. So that hopefully I've taken you through an arc of like an observation. Things aren't very stable, to we did some calculations. We covered different salts at different performance in the literature. We used the insight we came up with to design a new salt, and we validated that with the help of our experimental colleagues. I'll take you now to another example, and here we're looking at cathodes, not electrolytes. So, and specifically lithium transparent oxygen retaining cathode coatings. So commercial lithium-ion batteries today largely rely on layered materials in one way or the other. It's the parent compound lithium cobalt oxide, the NCAs and the NMCs that are being, and basically it's swapping out those transition metals in the layers. And the material works by and large by lithium extraction and charge and putting those lithium ions back in discharge. You might ask yourself, why can't we use anything but cobalt, manganese, and nickel in these things? And it has to do with the fact that if you remove all that lithium, if you choose any other transition metal, they by and large will go into the lithium layer and you will destroy the structure. So as you cycle the material, you will get less and less capacity. And as we can sort of compare it to a bit like a Jenga puzzle, like you remove some lithium from a layer and at some point it starts crashing all down. Now, we all know that cobalt is a bit of an issue. Cobalt has a fairly low world production. It also is being produced under conditions that we're not entirely happy with. So the industry has gone more and more towards nickel, high nickel containing cathodes. Is that a problem? Well, the problem is that higher nickel content comes with a number of drawbacks, both in terms of structural as well as chemical stability. High nickel containing compounds tends to come with a very high amount of oxygen evolution. They're unstable against oxygen release at high delithiation, so low lithium content. And you can imagine that this is likely to happen first at the surface, right? That's where the lithium goes out first, and you have no lithium left and you lose oxygen at the surface. That surface becomes also structurally unstable and it tends to actually transform to become more rock salt-like, more dense. So you're shutting down the lithium transport through that surface layer. It's not a great thing. So people really want to stop the oxygen from going out. It's also a safety issue. Releasing oxygen is the way of burning your electrolyte and eventually an event, as they call it, if the temperature increases. So how can we keep the oxygen from going out from those high nickel content cathodes? Well, people have suggested dopants and coatings. My group has explored both, but I'm really just gonna look at the coatings today because I thought coatings are an interesting thing. We don't always necessarily know how they work. So that was a question we had early on. How do coatings work? If I want a coating that lets the lithium ions through, right? Because that's my charge and discharge process. But I wanted to keep oxygen in. So I want it to be ion selective in its transport. One cation can go in and out, but the oxygen should just stay in there. So how do you do that? And how does that work? So if you ask people how do coatings work, if you really truly have a conformal, and the best thing would be to have an amorphous coating, because then you have no grain boundaries. It's all the same kind of disordered material that surrounds your cathode. There are different hypotheses on how does the transport go in that kind of material, and it probably depends on the material as well. So we looked at the different kinds of models that had been proposed in the literature. If you look at these thin conformal coatings, you could imagine an electron conducting model where you have a semiconducting material that basically transports your lithium ions with an accompanying electron that basically reduces the cations around it. Or you can imagine an electrolyte model where you have some extra oxygen hanging around because you're oxygen, rich or something, you have extra defects and you're not solvating your lithium ion, kind of like you do an electrolyte, and you're moving the lithium ion with that solvation shell that screens the lithium. Or the last one would largely be that you're just building up space charge on one side of the thin layer, and you're just tunneling your lithium ion through. We did some back of the envelope calculation, and so did Dane Morgan in his previous paper, basically convincing ourselves that the electric field from the space charge model would be higher than the breakdown strength of most of these materials. So that doesn't seem to be a viable model. But the two other ones, the electron conducting model and electrolyte model, we couldn't decide which one it could possibly be. So we decided to do both in our modeling and see which one made sense, or if they did either one of them. And here are some examples of the ab initio molecular dynamic simulations that we did of these amorphous materials. So we chose two models, aluminum oxide and zinc oxide. Aluminum oxide because it's very often used as a coating material, and people have suggested that it retains oxygen. And zinc oxide because it's very different. It's a semiconductor versus aluminum oxide is an insulator. So these hopefully would give us an idea of how these different coatings work. And what we found is that these amorphous materials, the way that lithium ions move, and that's on your left panel, compared to oxygen ions move, that's on your right panels, is largely by being stuck in some environments for a while, and the ions vibrate, and then they break some bonds, and then they hop to the next cage, and then they vibrate there for a while. So the activation mechanism, both for oxygen as well as for lithium, is this bond breaking, bond formation mechanism. It's not sort of a nice little like diffusion version. It's really quite dramatic. Like it sits there for a long time in one cage, breaks a bond, hops to the next, and keeps going. So it really is about how the coordination and the bond strength of between the cation, so lithium and oxygen, or the oxygen with the other cations in the material work. So how strong is that bond that you have to break, and how many do you have to break in order to facilitate or retain? Because remember, we want to facilitate lithium, but we really want to keep oxygen in there. So that's two different processes here. Okay, so here we have calculated the lithium diffusivity and the oxygen diffusivity as a function of lithium content, recognizing that maybe these coatings get a certain amount of lithium in them as the material charges and discharges. Who knows how much there is in there at any given time. So we wanted to make sure we understood that part too. And we have the two models, the lithium, the electron conducting and the electrolyte model. So two curves for each material and each ion diffusivity. And as you can see, for the first impression you have is that the gray curves are above the blue curves. Zinc oxide conducts both lithium ions and oxygen ions a lot better than aluminum oxide. Okay, that could make sense. The second thing that sort of strikes you is that most of the curves slightly trend upwards with lithium content. So the more lithium you have in there, probably you have higher diffusivity as well, but it's not as clear of a trend. And interestingly, aluminum oxide, which is highly insulating, you can see that the lithium ion diffusion is actually higher in the electrolyte model than the electron conducting model, because basically the electron conducting model in aluminum is pathetic. There is no electron conduction in aluminum, right? So the electrolyte model has to be the way that the lithium ions move in aluminum oxide, if they move at all. You could argue that maybe they don't, right? It's very low diffusivity. So, okay, cool. We now have some numbers to this, but what does this really mean if you were to look at it from a cathode perspective? Oh, maybe I'll go to some analysis first before I get to that. Okay, so I did say something about, well, the coordination environment matters. Oxygen tends to bind to its cations and lithium tends to bind to oxygen. So when we were looking particularly at the oxygen retention and we contrasted zinc oxide with aluminum oxide, we found that by doing the orbital analysis, there are a lot more bonding overlap between the orbitals in aluminum oxide than there was in zinc oxide, which gives us a sense that the bond strength in aluminum oxide between the oxygen and aluminum is a lot stronger than the zinc oxide. So bringing those bonds to activate the hopping between the different environments in aluminum oxide is going to be a lot harder. And indeed, the diffusivity trends such that if you look at the graph, lithium oxide has fairly high diffusivity of oxygen, zinc oxide sort of in the mid-range, and aluminum oxide, and interestingly, antimony oxide is even lower. So if you really wanted to retain oxygen, you've got to be down there with aluminum oxide and antimony oxide. So that's the sort of an explanation why, even though zinc oxide actually has more cations or the same amount of more cations per oxygen holding onto it compared to aluminum, right? There's 3 oxygens per 2 aluminum in aluminum oxide, but in zinc there's 1 to 1. The bond strength is really what seems to matter. Okay, so now let's do the back of the envelope calculation. Let's say that I have a 10 micrometer lithium nickel cathode particle and my coating is somewhere between 1 nanometer to 10 nanometers. And I calculate that it would be nice if my lithium didn't take more time getting through the coating than it has to get through the whole particle, right? My coating has to let the lithium ions through really quickly in comparison to how long it takes for it to get through the particle itself. So it takes about 600 seconds to get through the particle. And in aluminum oxide, if it's a 1 nanometer coating, it would take about 100 seconds to get through. But if it's a 10 nanometer coating, it would take 10,000 seconds. That's not acceptable, right? If you want a coating that doesn't detain the lithium, you have to stay on a very low, like 1 nanometer coating if you're conformal. If you have grain boundaries, all bets are off, because then they will probably go through the grain boundaries. And the oxygen is retained. You're good there. There's like, even with 1 nanometer, you're looking at it's not going to go. In zinc oxide, the lithium sips through like crazy. That's how much the diffusivity does, that higher diffusivity. So, you know, no problem letting the lithium ions through, but on the other hand, the oxygen is going to get through too. So even for a 1 nanometer coating, the oxygen will zip through just as much as the lithium through, almost. Well, 4 orders of magnitude, but it won't matter given that the actual charge and discharge will take 600 seconds. So in the end, what we've come up with here is a metric and understanding for how does the diffusion of lithium and oxygen move through these materials. It tends to do with the bond breaking, bond formation mechanism, and we can tune the lithium versus the oxygen diffusivities by looking at those bond strengths between the different parties. Among the binaries, the antimony oxide were some of the best materials we found, but we do think that polyanions and sort of tuning the coating chemistry a bit more, it will be promising. So that's what we're working on right now. Okay, that was the second topic. You guys ready for the third? I'm trying to sort of imagine that I have an audience in front of me and I'm sort of addressing the audience. Okay, so the last topic is the least developed, because this is something we're working very hard on right now. We're very excited about it, so I want to share that excitement. We're trying to predict the solid electrolyte interface formation, the SEI, which is a huge challenge because it's something we haven't understood despite decades of work in the battery industry. So the SEI is the heterogeneous, largely amorphous phase that forms when a very reductive anode, lithium metal or graphite, meets an electrolyte that doesn't have the power to withstand that reductive capability. So the electrolyte, when it meets the anode, is going to reduce, decompose, and form this gunk of decomposed matter on top of your anode. And if you've got a functioning SEI, that SEI magically lets lithium ions through, but keeps the electrons where they should be. So similar to your coating, except now it's not oxygen, it's electrons. So when you shut down the electron transport, you eventually shut down that reduction mechanism, and you're actually widening the electrochemical window of your battery, despite the fact that your electrolyte isn't stable at the underlying potential of that anode. So it's really quite magical. We have no rational way of designing SEIs today because we don't really understand how they work. We don't understand entirely the conduction mechanism. We don't understand entirely how they form. And we certainly don't have a way, if somebody asks you, can you come up with a way to do this from a priori, if you just give them the components. So we've started doing this, and we thought this time would be ripe for doing a cascade of reactions, a data-driven approach, where you literally calculate all the possible fragments that can form when you expose the different molecules and their solvation structures to the reduction potential of your particular anode. You look at all those fragments that can form, and you look how they can now recombine, and you see how you're moving towards thermodynamic sinks in the reaction cascade. And we were trying to sort of see, can we simulate that in any way? We have amassed a database of calculated energies for each of these reactions, the bond breaking as well as bond formation. We're also using machine learning to help us to gauge where to go, because it becomes a combinatorial explosion to look at all the possible fragments and their recombinations. We are using mathematical pathfinding algorithms to identify low-cost reaction paths, because there are tons of them. And we're using mostly thermodynamics now, but we are slowly building out our networks with transition states and kinetics. And again, we're going to use machine learning to see if we can infer activation energies based on those calculations. We can't calculate every single transition state. But the cool thing is that if we can do this, then we can actually do very long time scales, because it really just only depends on what species we include and our algorithmic efficiency. Because if I could go all the way to polymerization if I just included all those fragments and the recombination of different fragments into those different polymeric molecules. And the way to do this is that you get some help from your friendly mathematician community. So Dijkstra's algorithm will give you a very fast way of finding the shortest path in a graph network. And Jens' algorithm, so the n shortest path. So this is a great idea, and we're going to use it, but we have to adapt it for our chemical networks. So what these graph theories rely on is that if you have A, you can always form C in this network. But if you really are of the type 3 chemical reaction where you have A plus B goes to C, that is not taken into account in Dijkstra's algorithm. So we had to make sure that we had the cost for all these combined chemical reactions in the first place in an appropriate manner so that we can apply these mathematical pathfinding methods. So that's what some of my team has spent a lot of time on, trying to find a way to separate out these what we call prerequisite costs. If you are an A plus B kind of reaction and you're starting with A and you're finding your way to C, that's your pathfinding. But B comes in here, B comes with a cost, right? How did you form B? So solving this iteratively and separating out the nodes in a way to make sure that your network is fully characterized before you apply Dijkstra's algorithm has been the way for us to get to a reasonable result. We've done a lot of Dft calculations to generate all these different fragments. We take all of the molecules, and we have taken lithium ethylene EC, lithium FEC, linear carbonates, the salt, lithium PF6, water, and all the products we could find in the literature, starting out with lithium metal, which is the most characterized anode in the literature, to make sure that we have as many fragments in there as possible and as many products as we can identify today. And the fragments have to be unique, so we've had algorithms for fixing that, and also assuming that they can be reduced. So assuming not just chemical bond breaking, but also electrochemical bond breaking. We use machine learning because we can't form every bond. We possibly couldn't imagine the combinatorial explosion of breaking every bond and all these fragments that can form, and now allowing all those fragments to recombine in different ways, in different parts. So we're using machine learning to front load the ones that are more likely to be formed. And what part of my team has been doing is building this machine learning algorithm to predict bond formations and bond breaking based on not only the local environments in a molecule, which makes sense, is it a double bond, is it a CH bond or a CN bond, or what kind of bond is it, but also the global charge of the molecule, given that we're dealing with reduction events here, as well as just local chemical environments. It's been fairly successful. We have shown that our models work just as well as other just chemical networks and chemical machine learning models on existing data sets in the literature, and also on our own data sets, which is very, very large at this point. Okay, so let's go back to the promise. I know I'm getting a little close to time here, Piero, so I'm keeping track of it. We wanted to see if we can simulate the reaction cascade. We have thermodynamics, we have pathfinding algorithms. What we really need to do is actually validate this on something, right? We have some paths that are proposed in the literature. For example, the formation of LEDC from the ring opening of lithium coordinated EC. And if our network can completely a priori just get those pathways, then we have done something right? We haven't come up with something that is not in agreement with previous knowledge. So here is the path that our network found by itself, no human intervention, of the path from LEDC. So you see at the top there is a lithium coordinated EC molecule, the solvent. And when that gets reduced, it ring opens and goes through a cascade of decompositions and eventually reaches the thermodynamic sink of LEDC. The two paths this is a constructed network with 6,000 species, 4.5 million reactions, by far, as far as we know, the largest electrochemical network ever. And the two paths that have been proposed previously in the literature is the blue and the purple, the green and the purple path. And you can see that not only do we reproduce those two without telling anybody where to go, but we also get 3 more paths. And that to some degree, and they're not unreasonable paths, they're just slight tweaks. In some cases, you coordinate with another lithium, you combine two ring-opened EC molecules with lithium coordinated. So it really gives more of a flavor of how many ways you can reach that thermodynamic sink of LEDC instead of just one or two pathways. There are probably many roads to Rome. And if you think about this in a sort of kinetic Monte Carlo perspective, which is where we're going to, this cascade of letting water run in different ways, yes, it might run in the steepest descent, but it might also run in other ways. And it shows you the diversity of decomposition reactions. So we're pretty happy about that. And this is where we're going to keep on, see if we can actually predict what SEIs look like, how they form, in what sequence they form. But I'm just going to spend the last 2 minutes, and I promise it's not more than 2, to talk about the last part of how my group operates, and that's around dissemination. What do we do when we have data, workflows, and algorithms? I just gave you a snapshot of three things related to energy storage, but we have gone after a lot of different other kinds of materials. A lot of them have a clean energy hook, materials for carbon capture, magnetocalorics, thermoelectrics, photocatalysts. And in all these cases you see here, we've actually come up with materials that were first predicted from theory or this data-driven approach, and then later made in experiments. And all of this data that we use to predict these and all the algorithms are going into the materials project in one way or the other. And this is the website, and it's free. You can use it if you just have an email address. Currently, we have something like over 100,000 crystalline compounds. We have molecules, nanoporous materials, band structures, total dispersion curves, a lot of the stuff that I already talked about in the beginning. But maybe more importantly than how much data we have is the amount of people that use it. So every day, between 2 to 5 million data records are delivered around the world, every day from the Materials Project through its API. And that's, in my opinion, is a testament to how useful this data is to the community. If I just go through one example, if you click on one of our materials, you get the crystal structure, you get the phonon dispersion curves, if we have it, X-ray diffraction, it was the band structure, then the phonon dispersion curves, the Zanes, and X-subs is coming, both L-edge and K-edge, so characterization of materials, the elastic tensor, substrates, if you're doing epitaxial growth, then this gives you a way to analyze which kind of substrates are likely to give you your target compound, equations of state, similar structures. Again, the cool things you can do to analyze data and structures when you have a lot of it in the same place. Dielectric tensor, piezoelectric tensor, if that's applicable for your material, and the calculation summary at the end. And also, actually, we're starting to get more and more user contributions. So people who submit their data to the Materials Project, not things we produce ourselves, we're now, in a way, we are able to incorporate that. We have over 160,000 registered users with I used to use the word virally increasing users. I don't do that anymore. Doesn't feel right. But yeah, rapidly increasing users, something like 40,000 new users last year. And you can see the spikes of the number of millions of data requests we get every day. Sometimes it's like just hovering around 2 million, and sometimes we get spikes of 45 million requests. That's the big spike you see down there. So we're all over the world, and we're very happy to be a resource. And I'd like to end with thanking my group and our sponsors, and I'll be very happy to take any questions you might have. Hopefully I can answer them.
Okay. Thank you very much, Christine. We have about 107 participants. You don't see them. And it's also night over there. Okay, so thank you very much for spreading the virus of Materials Project. And, I think that's the best comment. We have now our discussion section, and I forgot to mention the name of the people that will lead the discussion session. Aaron from Imperial College is a professor of material science, and my colleague here in the Department of Physics is a professor, Kwek Sijin, and they will be leading the discussion with me together with Adam, Shafiq, and Antonio, if he wants. Thank you very much for the nice talk. The floor is open, and I encourage also people from the audience to ask a question. I will be happy to let them talk.
Yeah, I'm happy to kick off. So thank you, Kristen, for a really nice presentation and overview. And I guess the introduction, really reminded me of how rapidly things have progressed, I guess, over the past 20 years. So starting out, we're even calculating a simple metal. So solving the Kohn-Sham equations was quite challenging. And now we've access to these immense databases. But maybe just thinking about the power of databases. So I guess on one side, what you mentioned, that we can identify trends and perhaps previously overlooked candidates for particular applications or particular properties. But I guess the other side would be using that data to extrapolate to new chemistries. So I guess going beyond what's known. And would you be able to say a few words on how you see that direction going over the next sort of few years or decade?
Sure. I think we tend to put different buckets when we do materials design. The low-hanging fruit bucket is materials that have been overlooked but have been synthesized. They've just never been considered for that particular application. It's the easiest. If you go to an experimental colleague and say, hey, why don't you try this coating or this particular material? Here's the synthesis recipe from the literature. They're much more amenable to actually try to help you out in that situation. If you give them a material that has never been synthesized before, they look a bit nervous, to be honest. It could take years for them to make that material. We have done it. Like I said, the fluorinated carborane, but it's a little bit different in molecular chemistry. Functionalizing a molecule is a little bit easier than making a completely new inorganic compound. And one of the things, or the couple of handles we have on, so what I would say, what I'm doing with this ramble is saying that synthesis is a big deal, right? Trying to synthesize a completely new compound is an somewhat overlooked challenge when you're coming up with new materials. So what can we do from the computational perspective to ease the anxiety of our experimental colleagues in that point? Well, we always calculate the energy above hull, right? And what that means is that you have this basin of stable compounds, and if your new compound sits above that hull, the higher it is above that hull, the more challenging it becomes because there's such a thermodynamic driving force for decomposing it. So energy above hull is one metric. We found but it's not foolproof, right? We know that if you put your criteria at 100 MeV above the hull, you get 80% of all known oxides. So 20% are outside of that. So yes, it's reasonable, but it's only 50% of all known nitrites. So nitrites clearly have a much wider range of synthesizability or metastability. So how do we understand that? A couple of years ago, we formalized something called the Amorphous Limit, which basically tells you that thermodynamically you're very unlikely to make a material that is metastable with respect to the amorphous version of that chemistry, because you're usually synthesizing something at high temperature or something, and the amorphous material is going to win at some point. If you're if you're higher in entropy and in enthalpy than your target, and you then have the amorphous one is going to have a higher entropy, you're kind of screwed. It also speaks to nucleation to some degree. We're starting to get the sense that nucleation is this fluctuation between the melt, the amorphous state, and crystalline states. So if the amorphous state has a lower energy, what hope do you have of actually crystallizing it? You have no thermodynamic driving force. That helps, but the amorphous limit is pretty high in most materials. It's somewhere in the order of 200 to even an EV for carbon. Like, it's one of the reasons I think we can make so many different polymorphs of carbon, but it can be useful. So in silicon dioxide, if you look at all the zeolites out there, it's only 100 MeV per atom. So there you can probably screen out a lot of zeolites that are hypothesized. So yes, we can make and we can produce new materials. We have tried, we published them. It's hard for us to convince our experimental colleagues to make them. I don't know if you have another.
There are many online. I can see names. We have also Prof. Chitam from is hiding there, and I'm sure he would have some comment in that regard.
Ah, Tony.
I think Tony can make anything.
Let me allow to talk him. Yeah, he's here. I don't know.
Christine, but actually I think that what you talked about in the last part of your seminar right there is a step forward to perhaps for theorists to come up with proposals on how to synthesize a given material if it's really good.
Yeah.
Yeah, kinetic Monte Carlo and graph networks. Yeah.
Yes, basically synthesis pathways, trying to suggest the precursor, trying to suggest the temperature, or when you're most likely, what chemical potentials of your ingredients that you need to be at in order to promote this compound versus all the other competing things that are going on in the space. So we are working on that, but it's not easy because it is thermodynamics and kinetics. It's not just thermodynamics.
Right. In some ways, we would have to be quite judicious about the space of materials that we want to search as well, because otherwise we can come up with anything.
Yep.
Yeah. Yeah.
Yep. I once suggested a magnesium cathode that had two, you know this, Piero, remember the double substitution? That paper, that material, if anyone can make it, has an amazing mobility of magnesium, but that paper's been out for like, what, 7 years now? And I don't think a single person has made it.
Yeah. There are several questions from the audience. There are people, of course, machine learning is the topic of the day, right? So somebody is asking about, can you explain what algorithm are you using when you presented the formation or understanding the SCI formation?
You know, I should really point you to the paper because the details are in there and they're much better presented in the paper. It's a convolutional neural network, but there's some changes to it. I think the most important part is that we're doing differently than the other people that are including that have done bond formation or bond breaking machine learning in the past, is that we're including not only the local environments of the molecules, but also the global charge, because we're dealing with electrochemical reaction. We're also using not just the reactant, but also the products, because we're not using just homolytic, like, you know, non-charged to two non-charged fragments. Because we have a charge, potentially a charge on the first molecule, we can go A or B could either have one charge on the other and none of the other. So there's different varieties there. So we have to include what do you expect to come out of this as the machine learning model. So that's the big difference. And we had to make some changes to the machine learning algorithm to accommodate for that.
Actually, I was curious in that sense. So you gave it the target compounds, or the machine learning elaborate all the way from the A plus B all the way to C? Let's put it that way. Yeah.
So if you're making a bond, you kind of know what you have, right? You know this fragment and that fragment. So
okay.
unless they're dynamically unstable, so we do run them in DFT. They don't, unless they fall apart, then it's not a viable fragment, at least under those conditions. I agree that there could be other reactions with the solvation structure and other in the electrolyte, but like you have those two fragments now. But now you have to decide where the charge goes if you have a charged molecule. So you basically have two versions, and whatever is now predicted to be the lowest delta G, that's probably the one we're going to calculate.
So you consider all the radicals?
Yes.
Okay.
Yep.
Interesting. Okay. And we have another question asking how these machine learning methods compare to a simple linear interpretation. Sorry, not interpolation.
That's a good question. In my naive way, I think of machine learning as linear interpolation in some multidimensional space. So it's just, I mean, you have all these data points, right? And all the machine learning algorithm is trying to do is to fit all those data points in the best possible cost-efficient way, right? So it's just an efficient way of doing that. So it's not better, right? It doesn't have, in my opinion, extrapolative properties beyond what you give it. Mm-hmm. So you have to encompass the space that you're predicting within the space of your data.
Somebody is asking something related, and then I'll leave the floor to the panelists. Yeah, a question related to whether there are viscoelastic polymer structure in materials project, or maybe there is opportunity in the future to include this viscoelastic polymer, or polymer in general, I believe. Yeah.
Yep. I've been asked that many times, and I'll be very upfront and say that I'm not an organic chemist, but I have been working with some people that are organic chemists. So we worked with Brett Helms at LBNL to try to come up with recyclable plastics. We are still in the mode of operation where we're trying to develop methods that we can predict and understand what he's seeing in experiments. So we're still in this sort of data production workflow stage. Once we're at the point where we say, okay, now we actually do understand what we're doing, we have a predictive, robust algorithm, yes, that will probably move some of those structures and some of those algorithms into PyMetGen, Atomate, materials products on our API. So it might come if we're successful. if we're not successful, we might just publish a paper on how that didn't work out.
Well, it's always good to publish even negative results, right?
We should do more of that.
Yeah, don't keep it under the bonnet. Okay, so any more interaction from the panelists? Aaron?
Sure, I'm happy to ask a more specific question. So I thought the work on the SEI formation was very interesting, because I guess that's one of the big challenges for computational chemistry materials modeling for batteries, right? We're good at doing isolated components, but what happens at the interfaces is quite difficult. And I guess the thermodynamic analysis seems quite reasonable as a starting point. I think what always made me a little bit afraid about SEIs is sort of the non-equilibrium aspects. In terms of, you have these very highly, I guess it's a highly constrained problem in terms of the nucleation and growth of whatever SEI that forms. So I guess, as you said, you have kinetics, but I guess you also have strain coupling in as well, and maybe some local fields that are present. I guess you're starting, yeah, you mentioned your starting point, but how far away do you think we are from the full sort of complexity of what you can actually measure experimentally?
Yeah, no, you're absolutely right that I am only doing what I would call the sort of early formation of the SEI and the non-mechanical properties of the SEI. So there are other groups that are, so we're funded as a program, as we all are in the US, like a program out of the ERE in this case. And there's a component of that team that does phase field modeling and you know, fitting basically the data that we give them from an atomistic perspective into partial differential equations to try to get to some of that long-term evolution of mechanical properties, passivation, things that I can't deal with on my length scales.
Okay.
Yeah, I see.
Tony wants to make comments, and he wrote me. Yeah, he's
Tony,
here.
so good to see you.
Hi, Kristen. I'm just up the road from you.
Really?
So I'm in Santa Barbara.
Oh, okay. That's not really up the road, but okay.
Thank you for a fantastic talk. It's really impressive. I just wanted to come back to this whole business of, you know, unknown phases and what you might reasonably expect. And you mentioned the case of silicas, where there are a lot of polymorphs and a lot of zeolitic silicas and so on. And one of the things that makes it very difficult there is that the conditions under which you make them, you're not just making SiO2, you're making SiO2 with stuff in the cavity, solvent molecules, or amines in the cavities and so on. And so you can create networks which when you take the stuff out of the cavities are way above the, you know, the convex hull and way above what you might imagine as reasonable, and they just get trapped as metastable states because in the case of silica, silicon oxygen bonds are so strong, so it's not going to collapse into something more stable. And I don't know how you get around that problem, other than treating them one at a time and so on.
Yeah, no, I agree with you. How much kinetic stabilization we get is not clear. At this point, all I can do is talk about whether thermodynamic driving force, and I agree, it's silica bonds are not to be trifled with. I do think there are plenty of examples, though, when you take the moisture or the water or the solvent out of these systems, they do decompose. So there's got to be some limit when these things start to break anyway. So maybe that is not quite the amorphous limit, but somewhere around there, because breaking a few bonds and starting to sort of could happen over long time scales. I suppose that's the problem too. How long do you expect it to be stable and under what conditions? If you're just leaving it alone on your shelf in your laboratory, maybe 100 years from now, it'll still be fine. But what if you're asking it to do something?
Yeah, we once looked at that question and annealed something for about a year or so and ran a powder pattern once a month to see what had happened. And nothing happened, so we gave up in the end.
Well, that seems good enough to me.
Yeah.
You should tell me what structure that is, and I'll tell you if it fits within our amorphous stability limit. That would be an interesting case study.
I'd have to think back. I think it was one of our ZIFs. It was quite a long time ago.
Yeah.
And the other thing that I see as being challenging is when you've got a lot of closely related phases, close in composition, and the obvious examples are some of these kind of suboxides of transition metals. Like if you looked at TiO2 minus X, where you get to more or less continuum of phases, and understanding what will form and what won't form is challenging. And also, just recently, there's been a lot of work, of course, on TiMb207 as an anode, a new anode for lithium-ion batteries. And there are several other phases in that system. You get TiMb207, Ti2MB10029, and TiMb24062. Why on earth you get those, and then you don't get every other combination you can think of, I think still remains a mystery. I mean, that might be tractable for you.
Yeah, it's a question of how much do is there, I completely agree with you. One of the mysteries to me is we can calculate a lot of what we call hypothetical polymorphs of TiO2 that are within different energies above the hull. And brookite is quite up there, right? It's not particularly stable, and you got your anatase and rutile at the very bottom, but there's a plenty between anatase and rutile and brookite that, as far as I know, have never been seen. Why can't we make those guys? So is there, because it's an easy transformation between them and the other ones? Can we capture that to some degree in this infinite landscape of transformation paths, non-diffusive ones, or is it a diffusive one, in which case it's really difficult? Yeah. So I don't know, but I think you're right. I think we might be able to chip at it. You're not going to ask me to bark, are you?
I did consider it.
Later.
I thought I'd let you preserve your dignity.
I am.
We have a question from the audience, and the person is asking, making the statement that DFT is by definition a ground state technique, and so it would be less accurate to predict spectroscopic properties. How does Materials Project intend to standardize the errors or inaccuracies introduced by the fact that DFT is used in contrast to other higher-hand computational technique?
Yeah, that's a great question, and I think we deal with it already when we predict the band gap of materials, right? So the answer is that if the errors are, well, the way I deal with it, try to deal with it, it's not perfect by any means, is that if you're dealing with an ab initio code, at least in most cases, the errors are systematic. So if you imagine that we actually have a lot of data, for example, for X-ray absorption or for band gaps or something, and we correlate that with a certain amount of experimental data, really good benchmark experimental data, we can get a handle on how wrong we are. And if we're systematically wrong, hopefully within chemistries and structures, and we have to build those correlations, then I think we have an ability to interpret even slightly faulty DFT results. We've been dealing with it from long before. I mean, I remember when we started doing voltage calculations for batteries before we had +U or scan or any of those nicer functionals. And we were always consistently 1 volt below whatever people would measure. It didn't really matter that much because we kind of knew we were 1 volt below-ish. So we sort of like, okay, yeah, this is a cathode. We're predicting a 3.5, but it's going to be 4.5 or something. So again, I think what is so nice about DFT is that it tends to have that slightly systematic error to it. I hope that helped, but it's not perfect. It's not always completely easy.
I think in some sense the high throughput calculations are meant to do a quick scan, whereas once there are a few candidates that have been identified, we can do higher order methods to get a better handle of things. Yeah, and I actually had a question. So when one of the main purposes of the materials project is to be able to predict new materials faster than in experiments. And but in some sense, when we talk about low-hanging fruit, we start with the low-hanging fruit, and eventually we'll have to reach the higher up, the fruits that are hanging higher, and it starts to get a little bit more difficult, let's say, in terms of overcoming time scales and these kind of other issues with the accuracy. So at least from the past, do we have a gauge in terms of the time and also the cost, cost to buy the computers and to run the computers, how much savings that we can get over working in the experimental lab to find these, to get the same output?
That's a very good question. I just had one of my students calculate it. She was horrified to find out that her high throughput calculations produced more CO2 than going into the lab and making a compound. But she doesn't make 1,000 compounds, right? She just calculated 1,000 data points for compounds that have never been made. So it's very hard to put that on the same, because you have to then try to figure out how long does it take to make a compound. It could take anything from weeks to years, depending on how difficult it is. Whereas we kind of know to some degree how long it's going to take to calculate 1,000 materials. So it's very hard to make that calculation. But I got to tell you, my students are conscious of this. They're very serious about clean energy, and they felt very bad. Like, okay, let's not waste any calculations in the future, because it's not free.
Yeah, it's not free, isn't it? Yeah.
So let me so there is a question. Professor, thank you for your interesting talk. With regarding to the coating parts, can you explain a little more about your group work, like design of computational simulation and the analysis of the experimental results? I think this is a very open-ended question, so
Yeah, I mean, in the case of coatings, we developed first a workflow to try to simulate amorphous materials in the best way we could, knowing that you can't really simulate the variety of amorphous materials you can imagine with all the different short-range orders and long-range ways. So what we did is, okay, in Dft, right, you have to do a small box, 200, 300 atoms, and hope that, and what we did in that workflow was melt, quench, basically heat it up, quench it down with a scramble of atoms, but slowly bring that down to zero pressure and making sure we got something that was reasonable from a density point of view, because that we could compare to experiments. So once we had benchmarked that on a number of different compounds, we felt comfortable that this was pretty close to what we would consider a good model for amorphous materials. And then we ran ab initio MD for those amorphous materials, for those different compositions of aluminum oxide, zinc oxide, and antimony oxide, and all the other ones that we did in the coating project. And when we did the two different conduction models, in the case of the electrolyte conduction model, we included a whole lithium oxide, Li2O, right? Because we now had to have something that was charge neutral to add to that, which is effectively an oxygen defect plus the lithium that would now sort of solvate the lithium ion. Whereas in the other case, we would just assume that the lithium would move with an electron. So that's some amount of detail on how the coatings calculations were done.
Thank you. And yeah, so I think, I don't know, people are slowly fading out and there are still more questions, but they are a bit related to what you already answered. And I think we can, unless, yeah, somebody's asking if you use smileys for machine learning.
Yeah, smiles and selfies. What else we got out there?
Yeah. Yeah. And Heron and Tony, Xijing, Shafiq, more questions?
Thank you very much, Crispin, and that's a wonderful talk. Look forward to chatting with you in person when things are better.
Me too, very much so. I look forward to seeing you all. And if there are any questions I didn't answer, I'm very reachable. So just send me an email or something, and I'll be very happy to connect.
Thank you very much, Christine, and thank you all for participating. Have a good evening over there, and bye-bye.
Have a good day.
Thank you.
Thanks, Piero. Thanks, Aaron. Thanks.
Bye-bye.
Thanks,
Thanks, Christine. Bye.
Thanks, Su Ying.
Okay, thank you.